Okay, we're on the last final part 4, summary and application. So we're going to talk about the fact that all of your pieces come together, right? So you're not going to always just have a vertical stretch or a vertical compression or a horizontal translation or a vertical translation. They can all come together in one transformation rule. So this is what a general transformation rule would look like. It either will use H and K or C and D. They are interchangeable. Does that make sense? H and K, C and D are all interchangeable. Uh, because they're all interchangeable, uh, just keep in mind that they mean the same thing. Okay. Um, on here, we're going to dive in to specify a little bit more. But on the outside, I want you to make note of what is what. Uh, that your A and your K, these are what's affecting your on the your Y. So and that same term, A and D are affecting Y. Your B and your H, that's what's affecting your X. Okay. So we all know who's doing what, who does the role. On our first thing here, we have this is our full transformation rules sheet. So all of the rules in one location and how it visually and how it algebraically affects your function. Yes. All right. And so on here, I went ahead and wrote for you that your H and your K are interchangeable for your D and your C. So you may see that in the future, and that is A-okay. Remember that we talked about our first ones, our first translations were our vertical translations, and what causes us to go up and down. Next are how does that affect our coordinate? That means that we're adding or subtracting to our y, correct? On our next one was our horizontal translation. Our horizontal translations, we need to remember that our x's are what? X's lie. So your x's lie. All right, your x's lie. It appears that you are adding c, but you're actually moving to the left, which means that you're subtracting your c, the coordinate. It appears that you are subtracting c, but x's lie. So you're actually wanting to move right, which means that you're going to be adding. Yes. Um, okay, so I don't even know where I left off at. Oh well. Continuing. On to the next. So we have our negatives, which we just talked about. When you have a negative outside of the transformation, the function, that is a reflection across over the x-axis. That's because it is changing your y values. When you have a reflection, when you have a negative inside with the x, that is a reflection over the y-axis because it's changing your x's. I said x's twice, changing your y's. Sorry, here, changing your x's here. Um, Next is our compression and stretch for vertical. Your vertical compression, um, your vertical compression and stretch depends on the A, your coefficient essentially. What are you multiplying by? This is the factor. Um, it's a vertical stretch. If the absolute value of A, notice that it says absolute value, that means we do not care if A is negative. Does that make sense? You do not care if A is negative. You're just looking at A itself, the absolute value of A. If it's greater than 1, then that is a vertical stretch. If it's less than 1, but greater than 0, then that is a vertical compression. Okay. And so what that means is you're taking said A factor and you're multiplying all Y values by that A factor. All right. And then our B of X, F B of X, remember again, X's lie. They make things complicated. Okay. It looks like we're going to be doing the same thing that we're doing with our vertical, but we are not. Okay. Your B, it's on your horizontal axis. And if your B, absolute value of B is greater than 1, it is a horizontal compression. Remember, that's just playing the accordion, right? I'm applying more pressure, so I am compressing it inward. Okay. Horizontal stretch is between 0 and 1. It's the opposite of what you think with the vertical. Okay. Again, x's lie and make things complicated. So it looks like I'm multiplying by the b, but I'm actually dividing by the b, which means I'm multiplying by its reciprocal. Okay, we're multiplying by the reciprocal. Um, okay. All right. So if in terms of what we've learned and what this is referencing, if you're looking for a reference, so this first part, this is our part one notes. Our H is part one notes. Your negative, that is our part 3 notes. And then your stretch and compressions, those are our part 2 notes, where we dive a little deeper into all of it. All right, questions, comments, concerns. All right, that's our overview. Now we're going to dive into like function transformations, which are within our little putting it all together part notes. Okay. So function transformations, they can be written in a in a specific function format. So for example, for linear, our linear parent function, I can spell. Our linear parent function is y equals x. Agreed? That's just nothing happening, nothing transform around it. When we write it in function notation, all you're doing, you're only going to have pretty straightforward with linear because you only can multiply and add and subtract so much. But it would look like this. So for a linear transformation, you would have your A times, and you don't have a B. X minus, do I want to use C or H? Plus K. Sorry, X. Okay. When you look at the linear transformation, it is just basically, you want to know what that formula is called? No. Point slope. It's the point slope. It's point slope form. Okay. Quadratic. Your quadratic, I'm just going to write PF for parent function, is y equals x squared. That is an untransformed quadratic model. So its function notation form would be f of x equals a times, I need to make this a b, sorry, b times x minus h squared plus k. Notice that your here, your b has to be factored out. Your x has to be a leading coefficient of 1. So the b has to be factored out. So if this was 2, I would divide everything out by 2, and that would be my real h. It has to be factored out. Factored. The last one that we're looking at, our parent function for absolute value is y equals the absolute value of x. So y equals the absolute value of x. That's going to be f of x equals a absolute value of b times x minus h plus k. Okay, written in these forms or have these variables, you should be able to tell me what the function is doing without actually having to graph it. You can say, oh, my a is 2, so therefore it is being vertically stretched by a factor of 2. It's a linear function. It's a quadratic function. Okay, so we're going to practice doing that in our example. So here's our example that we have. It says find the function g of x that is finally graphed after the following sequence of transformations are applied to the graph of f of x equals x squared. Write in function transformation form and then write g of x. Okay, so starting off with what we have, it says if you, I'm sorry, before I get started, if you have your little chart, it's always good to have that out until you kind of remember what each thing does. So write the function transformations. We're going to start off with identifying our variables. If I am shifting right 3 units, what variable am I describing? H or K? I'm going right 3 units. I'm describing what? H. So this is telling me what my H is. Does that make sense? So my H equals 3. Okay. Next, reflect about the x-axis. If I want to reflect about the x-axis, what is it telling me? I'm changing the y value. Changing my y value means which one of my variables? My a. So my a has to be at least -1. And then I'm shifting down 2 units. That's going to be my what variable? My k. And k is going to equal what? I'm going down -2. So now that I have all of what they are, I'm going to go back here really quick. And I'm using the quadratic. I'm going to plug in what I know. Does that make sense? I know my a. I don't have a b, so do I have to worry about it? No. I know my h and I know my k. So I can plug in my function. Does that make sense? Okay. So it says first write it in a function transformation. Writing it in a function transformation is writing it in this format. So this is our function transformation. That means that the rule can apply to anything. Okay. So when it says to write in function transformation, you're writing it in this format. There's no equal sign. There's no of x. It's just this is what's happening. Okay. So we're going to do that. So based on what I have here, I have my a is -1 for this function f. There's no b. There's a 3 for the h. And there's a -2 for the k. So this is my function transformation. Does that make sense? So we have our a, our h, and our k. When I write it as g of x equals Now I'm plugging it into a quadratic function. I'm transforming the quadratic. So we have negative x minus 3 squared minus 2. And that is my g of x. It fell off. All right. Question. Comment. Yes. Oh, yes. Questions about the problem? No. There's no zero. If I put a zero, then it would cancel out the problem. Oh, one is Casper. He can be there or not be there. It doesn't change anything. Yeah. Because it says we're reflecting about the x-axis, and I think Jalen said that means that it's changing our y's. And so what changes my y's? Remember, we labeled what changes our y's? And our y's are changed by our a. So our a is what changes it by the signs. Our k is what causes it to go up and down. Other questions? Comments? Concerns? All right. Let's do the last one. Okay, so it has here. We have this function that has been transformed. It says that we have 1/2 x plus 1 squared. Find the domain and range of f. So it wants us to find the original. So, and then talk about h of x. So what was the original? If I was to take away all the transformations, what would my nakedness be? Take away all. It would just be x squared. So f of x is x squared. Does that make sense? I'm taking away all of the transformations. So I'm just left with x squared. And that is my parent function. Yes. It's just for this equation. It could be absolute value. It could be x cubed. It could be the square root. It could be, just depends on what function is being modeled. Okay. So when we graph this is a pretty quick graph. Remember, when you're graphing, your input values can be whatever you want them to be, but you should choose the smallest ones around the origin, correct? If your heart says, I want to go big, but I'm not. -3, -2, -1, 0, 1, 2, 3. And we know that those values, okay, this is my no writing zone. So my 3 has to be written real weird in the little corner because that's the only space that I can write it in. Okay. So -3 squared is going to give us 9. -2 squared gives us 4. -1 squared gives us 1, 0, 1, 2, and 9. So our parent function is here. You know, that's the most curvilicious thing happening. Yep. She's there. She's done. Yes. It's supposed to be a 4. Just got weird. As you can see, I graphed it at 4. I really can't even accept that graph. I was really trying to make myself believe that it was good. What the Hades, Bob? You know what? So that was better, I guess. All right. So there's my parent function. And the domain and range of this guy is what? What is my domain? It goes forever to the left, forever to the right, correct? And what is my range? 0 to positive infinity. My y values are greater than or equal to 0, correct? All right, so now it's describe and graph the function h of x. So how did h of x change? What, based on what we have this guy, and this guy. What happened to my parent function? Okay, let's identify with our 1/2. What variable is that? It's our a. It's our a for transformation. What is our +1 on the inside? It's our h. And what's our +1 on the outside? Our k. If you know what they are, then you should be able to tell me based on what's happening. Since our a is less than 1, we know that this is a vertical what? Compression by 1/2. Does that make sense? Okay, because our h is +1, we know that this is what's happening. We're shifting to the left 1 unit. 1 unit left. Because our k is a +1, we know we're doing what? 1 unit up. Does that make sense? So I know that when I graph it, compared to the purple, it should be compressed vertically, right? And then it should also be shifted up into the left, correct? Based on what I've described should take place. Make sense? All right, so we're going to do it. Again, you're the calculator, not the calculator. We don't need it. We got it. All right, so to find our new x, which variable is affecting our x? Which one of these affected our x? The h. The h is the only thing that affected our x, right? So that means to all of my x values, in order for me to go 1 unit left, what am I doing to those x values? I'm subtracting 1. So to all of my originals, they are being subtracted by 1. Does that make sense? So we have -3 minus 1. We have -2 minus 1. -1 minus 1. 0 minus 1. 1 minus 1. 2 minus 1. And 3 minus 1. Was it necessary to write them all out? No. I just want to make sure you saw what I was doing. So that puts me at -4, -3, -2, -1, 0, 1, and 2. Have my x's been satisfied? Yeah, right? Now we're going to do our h of x, which is our y. So what is happening to all of my y's? Well, there's 2 things happening, right? You have the a and the k to deal with, correct? So you have a and k to deal with your y's. When we are using PEMDAS, what do we do first? We're going to divide or multiply first, and then we're going to add or subtract, correct? So the first thing we need to do is our compression. So if I'm multiplying by 1/2, it's the same thing as dividing by 2. Multiplying by 1/2 is the same thing as dividing by 2, right? So we got to divide our y's by 2 and then make them go up. And how I'm going to make them go up? I'm going to add 1. Okay, so our y's have a lot happening to them. We got to divide them and we got to shift them. So we're going to divide by 2 and then go up 1. Divide by 2, go up 1. So you're doing that for each one of your y values. So let's talk our way through this. So let's start here with 9. So currently I'm at 9. I'm cutting 9 in half and adding 1. Does that make sense? So we have 9 divided by 2 plus 1. What is its new home? It's now going to be at 5.5. Agree? We have 4 divided by 2 plus 1. Where's its new home? 3. We have 1 divided by 2 plus 1. Where is its new home? Good. We have 0 divided by 2 plus 1. It's at 1. And then these are going to do what on the other side? Repeat because they are symmetrical. So I don't have to do the math again. I'm going to have 1.5, 3, and 5. So what I'm plotting, I'm going to make sure we're all on the same page. So our new points are going to be at -4 and 5.5, -3 and 3, -2 and 1.5, -1 and 1, 0 and 1.5, 1 and 3, 2 and 5.5. Do we see that? And if we did it correct, our graph should be compressed vertically and shifted 1 unit to the left and 1 unit up compared to the parent function. Okay, so we're plotting points now. Batman. Stop. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, that's a big half, but you see where it's at. I wanted you to clearly see my points. Do you see my points? Well, you're wrong. And bam. I got a little wider and shuffled a little bit. Did my domain change? No. Did my range change? Did my range change? Yes. Now what is my lowest point? At 1. And that is transformations. Oh my God.